variable, which is the quotient of two polynomials. And so this gives a conformal map of the sphere to itself. I mean, it's actually a branch covering. It's many to one, depending on the degree of this map. It has branch points, but away from the branch points, it preserves angles, and that characterizes these dynamical systems. And there's a similar sort of decomposition of the dynamics. There's some sort of set, which is typically nowhere dense, which is called the Julia set of the map. And this is, again, the locus of chaotic dynamics for this as a dynamical system. If you were to iterate the map, well, then its behavior is sort of chaotic on the Julia set, and off the Julia set it tends to be properly discontinuous, much like the action of the group here off the limit set. So the iteration of the map behaves in a predictable way outside of this sort of chaotic set. Okay, so
You're starting now.
Oh, we're starting now. Okay, so now I can begin the real lecture. So what I want to talk about is a criterion for the, I guess, a criterion for the breakdown of iterative algorithms for finding roots of polynomials. And the criterion is, we'll see that there's a sort of a topological picture that comes in that has to do with braids. There are certain braids that arise naturally in families of dynamical systems, and there's going to be a limitation on what braids can arise. And this limitation gives a criterion for the breakdown of iterative algorithms. Okay, but I want to start out by just talking about three-dimensional topology and drawing some analogies between rational maps and Kleinian groups. And there's sort of a finiteness property for quotient 3 manifolds, and sort of the key thing I need to carry out this discussion concerning root finding algorithms is the analogous property for rational maps. So I want to start out with just this topological discussion, maybe not go into it in too much detail, and then describe how this can be applied to limit the possible braids that arise in families of rational maps in a natural way. So I have some slides, but I'm going to probably write on the board too. These will not be big enough for you to actually read. So I'll sort of put them up and then maybe recapitulate what's on them. So if you have this quotient 3 manifold, one property it can have is that its boundary may be compressible. Now what does this mean? Well, let me just give you an example. Suppose you take a surface of genus 2 and you fill it in to make it into a solid object in space. This is what's called a handle body. Now, there's lots of non-trivial curves on a surface of genus 2, but it's possible that when you include these curves into the handle body, you can contract them within the handle body. So for example, this waist right here cannot be shrunk to a point on the surface of the handle body, but it bounds a disk through the middle of the handle body, so it can be shrunk away in there. So when this happens, the boundary of the 3 manifold is said to be compressible. You can compress this curve away. Now how can you tell when one of these hyperbolic 3 manifolds has compressible boundary? Well, the way you can tell is that if you were to lift this curve here up to the complex plane, what it would do is it would cut the limit set into 2 pieces. In fact, all the translates of this compressible curve would cut the limit set into many pieces.
Can you fix your drawing to indicate what you mean?
Yeah. So in this case, it turns out I can lift this compressible curve to the universal cover, to the boundary of the universal cover, and it separates the limit set into many pieces.
And this is a curve.
In any case, so the way you tell that this quotient 3 manifold is incompressible is that it has one of these, is that its limit set is disconnected. So this is actually characterization. So a 3 manifold has incompressible boundary if and only if its limit set is connected. Now these tend to good properties, these three manifolds with incompressible boundary. And the discussion is going to be partly about what happens when a rational map has a connected Julia set. That's in some sense analogous to a three manifold having incompressible boundary. Yeah.
I don't understand the picture. Are all the lifts of that curve circles? Is that what?
No, not circles. They're just some sort of Jordan curve.
Closed curve.
They're closed.
They are Jordan curves, not.
Yeah. This boundary just gets folded up in a nice topological way and becomes this surface.
I was surprised they weren't lines.
No, this curve. No, they're not.
The entire disk.
Yeah, you can lift the entire disk
yes.
to
Three-ball.
the three ball. Right.
Get a little cap inside.
And then there's a slightly harder theorem, Dane's theorem and the loop theorem, which allows you to conclude that this is if and only if. If you could separate the limit set by a loop, then you could actually find one of these compressing disks. So I won't go into that. That's three-dimensional topology. But in any case, the interesting thing is, well, over here in the Julia set case, there are many phenomena which are reminiscent of phenomena in three-dimensional topology, and we don't know how to construct sort of a three-dimensional object that it plays the analog for a rational map of this quotient hyperbolic manifold. Nevertheless, we can sort of say, well, when the Julia set is connected, that should have some of the good behavior of a three-manifold with incompressible boundary. That's going to be the result I want to discuss before going into the braiding. Now, there's a second property which is also quite useful. A slightly stronger version of incompressible is the following additional requirement. I just want to say this for completeness. I won't dwell on it. But there's the notion of a three-manifold being acylindrical. So if I take a surface across an interval, this is actually incompressible. There's no curve on one of these surfaces which bounds a disk in the three-manifold, because this is just homotopic to the original surface. However, there are certain funny things which go on. Namely, there's a curve on one end, one boundary component, and a curve on another one, such that within the three-manifold, these curves are the same. And the way you see they're the same is that they bound a cylinder on the interior of the three-manifold.
You should draw one around the other way. It's sort of a lot easier.
It would look more cylindrical. Right.
No, around the hole.
Oh, around the hole, right.
Right.
Okay.
There's a nice cylinder.
Okay, right. So here's a three-manifold which has a cylinder in it, sort of a non-trivial cylinder. There's a way to make that precise. In any case, you can see that there's this sort of phenomena. When this phenomena does not occur, the three-manifold is said to be acylindrical. Well, acylindrical carries with it implicit the assumption of incompressible boundary. And there's also a way to recognize this from the action of the group on the Riemann sphere. But I don't want to go on that. All I want to do is...
Well, this is a generalization because you have two curves which are homotopic in the boundary that become homotopic inside.
Yeah.
Which is sort of like the generalization of one curve
becoming homotopic to nothing. All right. Okay, now, when we have control over these two phenomena, that is, we don't have any of these cylinders, and we don't have any of these compressing disks, then there's a very nice theory of the mapping class group of these three manifolds. So the theorem is, this is due to Johansson, is that the mapping class group,
What does that mean?
I'll come back to that in a second, is finite if the three-manifold is acylindrical. And remember, acylindrical means incompressible and none of these non-boundary parallel essential annuli. So the mapping class group is the following. You take homeomorphisms of space to itself, but you only think of them sort of vaguely. That is, you think of them up to isotopic. That is, a homeomorphism is considered trivial and continuously deform it to an identity map of the three-manifold to itself.
Through homeomorphisms.
Through homeomorphisms. Yeah, through homeomorphisms, and everything is required to respect the boundary as well. So what this says is, well, here's an example where the mapping class group is not finite. For example, you can do a Dane twist around this curve here on one of these surfaces, and that whole thing just extends to the three-manifold by virtue of the existence of this cylinder. So what this theorem of Johansson says is that that's basically the only way you can get infinite order elements in the mapping class group. That is, there's lots of homomorphisms of these boundary components, but only a finite number of them extend to the interior three-manifold. So the three-manifold is complicated enough inside that if you try to twist the boundary, well, somehow the gut of the three-manifold are too inflexible to allow that thing to be extended to the interior. Okay, so that's the theorem in three-manifolds. Now, what I want to describe is a related theorem in rational maps. So let me recall the dictionary between rational maps finding group that are attached to the real lecture begun. So we have a rational function f and finding group gamma. There's the g set corresponds to the limit set. We don't know what corresponds to the quotient three-manifold. Then there's the automorphism group of f. This is a group of Mobius transformations which commute with the rational map f. So the automorphism group f is the set of Mobius transformations f such that m composed with f is equal to f composed down on the whole Riemann sphere. Now, it's not hard to see this is actually a finite group of Mobius transformations and a very simple structure. And this manifold has this metric of negative curvature, and an isometry of it lifts to an isometry hyperbolic 3 space, and the isometries of hyperbolic 3 space are just Mobius transformation. So isometries of the three-manifold are reflected in the sphere infinity by Mobius transformations sort of commuting with the group, and so I decided that that should be analogous to the automorphism group of a rational map. Now, what I'd like to understand is more flexible automorphisms of a rational map, and these will correspond to the mapping class group of the quotient three-manifold. So let me say that there's two candidates for what the mapping class group of a rational map should be. Let me describe the one I'm most interested in first. I may come back to the other one. Take the action of the map on its Julia set. So we just consider it as a dynamical system on the Julia set, forgetting about what's going on the remainder of the sphere. A lot of the interesting dynamics is on this typically nowhere dense set where the map is sort of chaotic. And now let's consider basically homeomorphisms of the sphere which commute with the dynamics on the Julia set. So I'm not going to require that they commute on the whole Riemann sphere, just on the Julia set. So I'm going to consider homeomorphisms of the sphere with the property that phi composed with f of z equals f composed with phi of z for all z in the Julia set, and the further requirement that phi actually be a quasi-conformal map of the whole sphere. Now there's lots of slop to my choice for such a map because I haven't made very many requirements about how it should be specified off of the Julia set. So the group of interest is actually the group of these maps modulo isotopy. That is, I consider two maps to be the same if you can deform one into the other through maps enjoying these properties. And that's just like the mapping class group of a three-manifold in some sense, because here the homeomorphism of the three-manifold lifts, and it gives you an automorphism of the sphere which commutes with the dynamics on the limit set. And this map is only, in the mapping class group, these maps are only required to be determined up to isotopy, and so similarly, the maps you see on the three-sphere are only required to be determined up to isotopy.
So the lifts don't quite commute, they sort of quasi.
They commute exactly on the Julia set, and they sort of quasi-commute off.
No, the tiny group case. They commute up to the automorphism induced.
Yeah, that's right. That's right.
Slight formal difference.
Yeah. Well, since this is just supposed to be motivation, so I don't want to be later making this exactly correct. Okay, so now the theorem, which I think is reminiscent of Johansson's theorem, is that if the Julia set is connected, then this group is finite. So I denote this group by mod JF. The mod comes from the fact that it's reminiscent of a modular group for Teichmuller space. And the claim is that this group is finite if, well, actually two things are satisfied. First, the Julia set is connected, and then there's a technical condition, which is that J carries no line field. Now there's only one very special example known in which this extra hypothesis is actually necessary. So I don't want to belabor what it means. If you like, if you want a precise statement without any further definitions, you can just replace this condition by J. The Julia set has area 0. So in any case, under a condition which is reminiscent of incompressible boundary for 3 manifolds, which is at least half of Johansson's criterion, we find that some analog of the mapping class group of the Julia set is actually a finite group. Now more is true. I mean, when you have this finite group, you say, well, what finite groups do I know arising naturally as automorphisms? Well, namely, there are finite groups of Mobius transformations. And so the claim is that you can take this map and deform it until these elements of the mapping class group become actual conformal automorphisms of the map. So informally, there's some deformation G, which is in some sense equivalent to F, such that under this deformation, the automorphism group of G becomes identified with the mapping class group of F. So this is in Johansson's situation, there's a similar theorem, namely, you can take this 3 manifold with this finite mapping class group, and you can deform it until all of these elements can be actually realized as isometries of some deformation of the original manifold. So often, this is sort of a Nielsen realization phenomena. Often when you find a finite group, you can deform the situation so all elements of the group simultaneously become isometries in the underlying situation. Okay, now there's a slightly stronger version of this theorem which I really need to do the discussion of grades. And it comes from the observation that the definition of this group makes sense even if the Julia set is replaced by any set in the plane, such that that set is mapped into itself by F. If I have such a set, then I have a dynamical system, and I can construct this group of mapping classes, things commuting with the dynamics on K. And the case I'm particularly interested in, again, has a connectedness hypothesis. So if K contained in J is a connected component of the Julia set, so the Julia set can be all over the place, sort of like a Cantor set in many pieces. Well, I take one of the pieces, and let's suppose that it's mapped into itself by the dynamics. Then the theorem is that, in fact, this little dynamical system here, this component, and the rational map carrying it into itself, is actually the same as the dynamical system of a rational map on its whole Julia set. So this dynamical system, just a component of the map of the Julia set which is preserved, is in some sense equivalent to the Julia set of another rational map, usually of smaller degree than F, and the action of that rational map on its whole Julia set. And furthermore, under the assumption that K carries no line field, or has area 0 if you like, this group is connected. K is connected. It's a connected component of the Julia set. This group is isomorphic, can be chosen to be isomorphic to the automorphism group of G. Let me just give a quick example of what this automorphism group business is about, because let's just take the map f of z equals z to the n. I just want to give an example of what this finite group of Mobius transformations is. So what are the Mobius transformations that commute with z goes to z to the n? Well, one of them is rotation by an n minus first root of unity. So if m of z equals zeta z, where zeta to the n minus 1 equals 1, then f of m of z is equal to zeta to the n, z to the n. So this is equal to zeta z to the n, so zeta to z to the n minus 1 is 1, and so that's equal to m of f of z. So that's one Mobius transformation. It actually generates a cyclic group of order n minus 1. And another one is, say, n of z equals 1 over z. 1 over z to the n is 1 over z, quantity to the n. And so these two things generate a dihedral group which commutes with the dynamics of f. And let me just mention as sort of an exercise if you want to think about this. You can make sense of the quotient of a rational map by a subgroup of its automorphism groups. And in this case, if you take the quotient of z to the n by this dihedral group, which forms its automorphisms, what you get is the Chebyshev polynomial of order n. Okay, so you can form this quotient much in the same way. If you had a 3-manifold and a group of isometries, you could form the quotient 3-manifold.
You form the quotient of the finite group acting on the sphere?
Yeah, this acts on the quotient of the sphere by this finite group.
And that's the sphere?
Yeah.
Is it always a sphere?
Yeah. It's an orbifold. It's a Euclidean da-da-da. But these finite groups there's only a small number of these finite groups. They're dihedral groups, cyclic groups, icosahedral group, tetrahedral group, and octahedral group. Okay, so that's the statement. Now, I want to show an example of why this bit about the component is slightly subtle. So here's an example of...
bit about the component? This theorem?
Yeah, this theorem right here. I want to show an example of how the dynamics on a component of the Julia set can be sort of surprisingly well buried in the dynamics of the rational map as a whole. So here is an example of a rational map. The formula is on the top. This rational map has the property that its Julia set is homeomorphic to a Cantor set across a circle. So if you were to draw a cross-section of this set here, this is the Julia set in black, what you would see would be a Cantor set.
So there is a smallest circle there?
There is a smallest circle. If you were sitting close enough, you could see there's a smallest circle. Now, the interesting thing about a Cantor set is there are only a countable number of endpoints to the Cantor set. The Cantor set is an uncountable set. There's only a countable number of points which are on the outside, which touch complementary intervals to the Cantor set. Well, similarly, in this picture, there's only a countable number of these circles which actually touch components of the complement of the Julia set.
Is this an actual computer picture of the
Yes.
Julia set for lambda equals 0.001?
Yeah. Now, there's this uncountable collection of circles, and only a countable number of them touch the outside of the Julia set. Some of them are just completely buried inside. They look like, close up, they look like this. They're not in the boundary of any component of the complement. And it turns out that among those, there's actually one which is fixed by F. So there's a very special component here, which I've sort of sketched in red. I don't know if you can see that, but in any case, it's sort of not in touch with the dynamics of F on the Riemann sphere, because it's completely buried inside the Julia set. Nevertheless, you can surgically remove most of the dynamics and make this into a rational map, such that the Julia set of that rational map becomes this formerly buried circle, and that's the entire Julia set of the rational map. In fact, if you want to understand this map a little bit better, it's not too hard to see what the dynamics is. It's basically, there are two annuli, an outer annulus and an inner annulus. They're each mapped to a much larger annulus containing the original two, and the map on the outer one is very close to z goes to z squared, and the map on the inner one is very close to 1 over z cubed. So in any case, when you do this restriction, as claimed in this theorem here, what you get for j of g and g is just 1 over, you get the Julia set as a circle, and the map G is 1 over z cubed. And this automorphism group, again, becomes a dihedral group of order 4.
In this case, the degree is the same, though.
No, this map is, the original map is degree 5. And the formula for the map is z squared plus lambda over z cubed. And that's actually a degree 5 rational map. And so, yeah, you lose a considerable amount of the map when you do this searching operation. Okay, maybe I'll skip that for a moment. Okay, I'm going to pass on to the grade discussion. So those of you who were here a year and a half ago have heard me talk before on a problem of Steve Smales concerning what kind of reliable algorithms exist for finding roots of polynomials. And these algorithms use rational maps, iteration of rational maps, to find the roots. And so the best example of such an algorithm is Newton's method. Smales' question is sort of motivated by what algorithms in the same genre as Newton's method are reliable for finding roots of polynomials. Okay, so maybe I'll recall these on the board since this is kind of small. So Smales' definitions are the following. A purely iterative algorithm is a map from polynomials of degree d into rational functions of degree k, assigning to each polynomial p of x a rational iteration t sub p of z. So that what you're trying to do is find the roots of polynomials. And this algorithm looks at each polynomial, and in terms of its coefficients, it writes down a rational function. And then the way you run the algorithm is you take this rational function and you iterate it on a random starting guess. So the algorithm is said to be generally convergent if that works for most choices of polynomials in starting guess. So the definition of general convergence is that under iteration, this rational function converges to a root of the polynomial. And this has to hold for all p and z in a dense open set of full measure. In the space of polynomials cross initial guesses, so in polynomials of degree d cross the complex plane. Okay, so this is what you would like a reliable iterative scheme to do. It gives you a rational iteration such that if you pick a starting guess at random, well, you almost certainly find a root of the polynomial eventually. I'm not requiring anything about the speed of convergence or something like that. Okay, so examples of purely iterative algorithms which are generally convergent. Well, the first one is Newton's for quadratics. This turns out to be quite a good algorithm. And secondly, there's a method for cubics. The formula is on the slide. I won't take the time to write it down. And these two methods, which work for degree 2 and degree 3, these have an additional property. So in my definition, I didn't require anything about the rate of convergence. But these algorithms have an additional good property. They're robust. So what does robust mean? Well, robust means that these rational maps, T sub p, are what are called expanding, or axiom A, or hyperbolic. In any case, what this this additional property implies that the global dynamics of these maps are quite good. An example of what these additional properties buy you is the following. If I have my roots of my polynomial, and I pick any neighborhood I like of them, well, then I would hope that only a small number of initial guesses fail to get this close to the roots after a certain number of iterations. Well, robustness gives you the following sort of nice asymptotic estimate, namely the spherical area of the set of initial guesses such that after n iterations, you're still not in this open set U, which I've drawn here around the roots. So this is the set of initial guesses that weren't good even after n iterations. The area of these initial guesses goes down geometrically. It's big O of lambda to the n, where lambda is some constant, which is strictly less than 1. So there's this notion of a robust algorithm, which I don't want to give a precise definition of, but it implies that the good global properties of the dynamics. It pushes away by a definite rate from the Julia set. The Julia set, the chaotic set, is the set of points which don't converge to any roots. And these additional properties imply that you don't stay near that set very long. You quickly are pushed towards the roots. And incidentally, as far as this geometric estimate goes, in case 1, you can actually take lambda equal to 1/2. And now, in case 2, I don't know a good estimate. It appears to be quite robust, but I don't know a concrete estimate for how robust it is. Okay, now, so a year and a half ago, I discussed a result which says that if you try to go up to degree 4, you can't write down anything on this side of the list. There are no algorithms which are generally convergent if you try to find roots of polynomials of degree 4 or more. Now, the proof of this was very unrevealing. It doesn't show, for example, where these algorithms break down. In fact, it was conceivable, given the nature of the proof, that you could have sort of the space of polynomials of degree 4, and there could be within this space one tiny little set of exotic polynomials for which your algorithm fails. And that as long as you avoided this exotic set, your algorithm would have good behavior, might even be robust in the sense I just described. And for example, it didn't even assure that every algorithm fails in a neighborhood of the polynomial p of x equals x to the d. So as far as the original proof was concerned, it was conceivable that there are algorithms which work near the specific polynomial p of x equals x to the d, even though they don't work on the space of all polynomials of degree d.
Why is that nice to know?
Okay, if you had an algorithm which worked near p of x equals x to the d, well, it would be just as good as an algorithm which works everywhere. The reason being, you could take your polynomial, x to the d plus a1 x to the d minus 1, and so on, and you could change variables so that these coefficients became quite small. You could just change by a linear scaling, replace this polynomial by p times x, alpha to the minus d. And if you choose alpha appropriately, these coefficients will become quite small, and all that will happen is that the roots are scaled by some factor. So if you had an algorithm which worked nicely near x to the d, well then it would be just as good as an algorithm which works everywhere, because you take your polynomial and you scale it first so that the polynomial is near x to the d, and then you apply your algorithm and then you scale back to get the roots. That would be a perfectly robust procedure, and that's not ruled out by this analysis. Okay, so I wanted to find a better explanation for why algorithms fail in degree 4 or more. And the explanation is in terms of something you can do with 4 points on the sphere that you can't do with 3 points on the sphere. And so it has to do with braids. So let me just sketch sort of what the overall discussion is going to be like. The point is, if you have an algorithm which works, well then, your picture of it is the following. There's some Julia set where things are not converging, and then there's the roots of your polynomial, say there are 4 points, and then a reiteration points outside of the Julia set tend towards these roots. Now as you move around in the space of polynomials, you don't know much about what's happening with this dynamical system. But it turns out that there's a result which says if you don't undergo some sort of drastic bifurcation, which causes your algorithm to fail and forces it not to be generally convergent, then this whole picture, in sort of a loose topological way, moves along as the polynomial varies. That means that this rational map dynamically has to follow the motion of these 4 points on the Riemann sphere. Now, what is a motion of points on the sphere? Well, it's a braid. And so what I'm going to describe is certain braids which cannot occur in this way. That is, they cannot occur by following the dynamics of the attractor of a rational map as you go around in the family. So it turns out that any braid you like can occur in polynomials of degree d by following a path around, but not any braid can occur by following the attractor of a rational map as you go through a deformation.
Can you say what a braid is?
Yeah, so I'm going to describe what a braid is. So a braid is just a motion of points on the Riemann sphere.
Periodic one?
So you have, yeah, it's a motion such that they come back, the points come back to the set where they started. The points are not individually required to come back to where they started, but they're required to come back to the positions at which they began. So here's an example of a braid. There's a time parameter which goes from 0 to 1, and then here's a picture of the Riemann sphere. And then as the time parameter varies, these points move around on the sphere, and I've sort of drawn the graph of their position versus time. Now the points are not allowed to collide with one another. They're required to remain distinct, and that keeps the strands of the graph separate, and that merits it being called a braid. So you see something where these strands go around and wind around one another, but they never actually physically cross or collide with each other. So this is what a braid is, and the requirement is that the set where you start and the set where you end has to be the same set. And furthermore, formally speaking, two braids are considered the same if this picture is sort of topologically the same. Now, I claim that whatever picture I draw here, I can realize this picture by the motion of the roots of a polynomial around some path in the space of polynomials. So let me try to make this picture more precise. Suppose that these four starting points here are the fourth roots of unity. They're the roots of x to the fourth minus 1. So the roots of x to the fourth minus 1 are four equally spaced points on the unit sphere. They're just 1, minus 1, I, and minus I. So that's going to be the starting and ending motion for this braid. So now I claim that whatever braid I draw here, I can realize it as the motion around a loop in the space of polynomials of degree 4, such that the path begins and ends at the polynomial x to the fourth minus 1. The way to do that is very simple. At each point in time, you have 4 points on the Riemann sphere. You write down the polynomial that has roots at those 4 points. This gives you a family of polynomials, and it begins and ends at the polynomials whose roots are the fourth roots of unity. So this shows braids correspond to paths in the space of polynomials. Now there was a condition. That was that the strands never cross. What that means is that the polynomials that appear along this loop are not allowed to have multiple roots. Multiple root corresponds to these strands coming together. So actually this loop appears not in the full space of polynomials, but in the polynomials minus the discriminant locus. The discriminant locus is the set of polynomials that have multiple roots. It's a complex hypersurface in the polynomials of degree d. Okay, so these braids, they correspond to loops in the space of polynomials of degree d minus the discriminant locus, and any braid can arise. Now, when you have a braid, there's a slightly weaker piece of information you can extract from it. Namely, you can extend the motion of these finite sets of points to a motion of the whole Riemann sphere. So for example, I can consider the following simple braid. So all I've done is I've taken 2 points on the Riemann sphere and I've interchanged their positions while leaving the other 2 fixed. Now, I want to extend this to a homeomorphism of the whole Riemann sphere. And the way to do that is I just do a half-Dane twist around these first 2 points on the Riemann sphere. That is, there's a homeomorphism, which is the identity here, and then does the following in the region containing these 2 points. It twists by 180 degrees in this annulus here, and then on this inner disk, it's just a rotation by 180 degrees that interchanges these 2 inner points. So given a braid, there's a way to extend it to a homeomorphism of the whole sphere. You just extend the motion to a motion of the whole sphere. And
give it a simple braid. You concatenate these on.
Yeah. And so when the sphere comes back to itself after this motion, you have a self-homeomorphism of the sphere. And it carries the initial points of the points in the braid to themselves. So it's a homeomorphism of the sphere sort of with these marked points to itself. Now the extension of the motion is not very well defined. I could be sloppy here, but it turns out its isotopy class is well defined. That is, it's well defined up to deformation through continuous families. So again, it's an element of the mapping class group of the sphere with 4 mark points. So I take it here and I push through here. I see at the end a homeomorphism of the sphere to itself with 4 mark points. Okay, now what I want to do is define the notion of family of polynomials which has complicated enough topology that no rational map is flexible enough to follow these roots as they go twisting around one another. So I want to define the notion of a complicated set of polynomials. So I'm going to say a set.
No family of rational maps.
Sorry?
No family of rational maps can follow.
Yes. Can follow these polynomials, the roots of these polynomials
In the sense
around.
that they're attracting things.
In the sense that their attractors stay within the roots of the polynomial. So I'm going to say a subset of the polynomials is tangled if the following is true. Well, I pick a base point, and I go to that base point, and that gives me a subgroup of the mapping class group of the sphere punctured at the roots of the polynomials. Okay, as I described, when you go around a loop, you get an induced monodromy transformation, a self-homeomorphism of the sphere punctured roots, and so this gives you a subgroup of the mapping class group of the sphere with mark points at roots of the polynomial. And the condition on this set is that the group you get here has 3 properties.
G is the image of
G is the image of the fundamental group of this set, which I want to be tangled in the mapping class group of the sphere with the roots marked. So the first condition is that G is transitive on the roots. What this means is that by going around a suitable loop in the space V, I can move any root to any other root among the roots at the base point. Okay, so by following, if the base point was x to the 4th minus 1, by following some particular choice of path, this root that's followed along might eventually come back to that root. And I can permute any root, I move any root to anywhere. So I ask that this group action is transitive on the roots. Secondly, I require that the group action is irreducible. I'll give a picture in a moment to explain what that means, and finally that the group is infinite. And the discussion is going to be, in the fail, to be, the reason that we break down on such sets is that first two conditions will get me in a situation where I can apply this finiteness theorem I just began. And the finiteness of the modular group, mod k of f, will contradict condition 3, that this group here is infinite. Okay, so this is just a notion to say that a subgroup has rich variety of grading going on in it. Okay, now this is what reducible means. An individual braid is reducible, and if you can find sort of a less complicated braid, which forms a big tube enclosing portions of the braid, as shown here. So it means that I can enclose the braid in a non-trivial tube so that there's more than one strand in each component of the tube, and that the guys that are, if you look at the beginning and the end, well, this tube consists of a collection of simple closed curves on the sphere, and reducible means that those simple closed curves come back to themselves after the motion of these roots. Now this can be phrased in terms of the mapping class group directly. It says that
every element to be reduced.
Sorry?
So
this is the notion of what it means for a single braid to be reducible. And one way to say this is that if I draw these simple closed curves here, which are roots into these small subsets, well then as I push them along, they come back to themselves. So they may be permuted, but as a set, they come back to themselves. This set of two simple closed curves here comes back to itself after going the braid along. And so this gives sort of a reduction of this particular braid. And I say the whole group is reducible if there exists a system of simple closed curves like this, which is preserved by the entire group, by every element of the group.
Is this the same as the group action on the points being primitive?
Almost. Does primitive mean it preserves no partition?
Yeah.
Yeah, I was just going to say, it says underneath this, I didn't know that was called primitive. There's an easier way to check these conditions. I'm going to give you see, you could just say, look at the action of the group on the roots itself. So that's some group of permutations. And actually, you can find conditions on that group of permutations which assure that this set is tangled. That is, assures that these more topological conditions are satisfied. So, well, transitivity, the first condition is clearly just a combinatorial condition. It's that this symmetric group, this subgroup of the symmetric group is transitive. And now irreducible, well, it's not equivalent to, but it's implied by the condition that the combinatorial group preserves no partition of the roots.
What's the combinatorial group?
So you just look at the roots, and as you go around the loop, they come back to the roots, and so that induces a permutation of the
the
roots.
image of the symmetric.
Yeah. Right, so it's the image of the monodromy in the symmetric group. And in this example, there's a partition of the roots into two subsets, each of 3 elements, and that partition is preserved by the monodromy action. So if that condition is satisfied, well, then the group is topological is reducible in this. As you can see from close curves, you can cook up a partition which is preserved.
But that's just the way you don't have to check it that way.
You don't have to check it that way, but in some sense, this is much more. This is a finite group, so it's more practical to check. And finally, well, if you want to measure that the group is not finite, there's a theorem of Zishang, partial solution to the Nielsen realization problem, which says any finite subgroup of the mapping class group be realized as a finite group of Mobius transformations. And that implies it's isomorphic to the symmetry group of some Euclidean solid. And those symmetry groups are either the cyclic group of order n, the dihedral group, the symmetries of a tetrahedron, a cube, or a dodecahedron. There's a small list of groups which are possible candidates for finite groups of a mapping class group. So if the combinatorial group avoids one of these finite groups, then the original group can't possibly be finite. So here's some combinatorial conditions which imply the more topological conditions. Okay, well, let me give you some quick examples of tangled sets. So suppose we're in polynomials of degree 4 or more. Well, then any neighborhood of x to the d is tangled. So x to the d, that corresponds to the polynomial where all the roots have coalesced to a single root. So if you're near there, well, as you move away slightly, they all separate, and then they can sort of be spun around each other in an arbitrary way. So they're all just staying near one another. So in fact, in this situation, you can easily see near x to d, the monodromy generates the full symmetric group of permutations of the roots. And so the first claim is a special case. The second claim is that this combinatorial group, the combinatorial monodromy group, is equal to the full symmetric group of the roots, then it's tangled. And the reason is S4 satisfies all the properties I just mentioned. It's transitive, it preserves no partition, and it's not equal to one of the possible candidates in the finite group of Mobius transformations. Finally, if you know something about mapping class groups, you can actually find paths in the space of polynomials such that a neighborhood of that single path is tangled. And here's an example of such a path. So the technical condition is that it's a path which, such that the monodromy is transitive on the roots. That means it's a cyclic permutation, transitive cyclic permutation, and it has to have pseudo-anosov monodromy in the mapping class group. Well, I won't say what that means, but here's an example. You take the first two, you sort of linearly order 4 roots. You take the first 2 and you interchange them, just locally. Then you take the next 2 and you interchange them. And then you take the bottom 2 and you interchange them. Well, that's clearly a cyclic permutation, and one can also show that this is what's called a pseudo-anosov element of the mapping class group. So these are 3 examples of sets which satisfy this purely topological property. Okay, so finally, what is the theorem about these sets? It's that, first, if you have one of these tangled subsets of polynomials to degree b, then every purely iterative algorithm fails on that set. That means there's some open set of polynomials, an open set of initial guesses, an open set of polynomials lying in this set, such that those initial guesses are bad for this set of polynomials. So this says, here's a purely topological criterion for many subsets of polynomials where no purely iterative algorithm can be generally convergent. Now there's a slightly stronger statement having to do with robustness. So we saw that in degrees 2 and 3, we can find robust algorithms. So the slightly stronger statement is that essentially no matter how you weaken your dependence on P, if you require that your algorithm be a rational function of Z, then there's no hope of finding robust algorithms which are generally convergent on these tangled sets. That is, there's no...
The coefficient could involve coefficients barred and...
Yeah, suppose I allow algorithms which depend on the polynomial in any way I like, as long as it's continuous. Okay? In the original discussion, they were only allowed to depend rationally on the coefficients of the polynomial. Well, if you're really interested in robust algorithms, you can prove a theorem which says no matter how the algorithm depends on p, as long as the dependence is continuous, the algorithm must fail somewhere on one of these tangled subsets, as long as it's a rational function of z. So basically, the moral is that rational functions are not really flexible enough to be robust iterative algorithms. You really have to go to smooth functions to get robust iterative algorithms. Okay, well, let me give a two-minute proof of this there. So the proof is like this. So here's a picture. There's the red dots are the roots of the polynomial, and the black stuff.
Four of them, right?
What? There's four.
Yeah, okay, I see that.
And the black stuff is the Julia set. Now, given this picture, I'm going to draw from this picture a bunch of simple closed curves in the complement of the roots. And the way I do that is I just go near the edge of each component of the complement of the Julia set, and I draw a simple closed curve. So for example, here's a component of the Julia set which sort of encircles these 2 points here. So it gives rise to one circle here. Now this component, well, on the inner edge, I get a simple closed curve. So I've drawn a little loop around that root there.
What are the two pictures?
This is a way of canonically associating to a closed set in the complement of the roots a collection of simple closed curves. And the way you do it...
The green ones are the simple closed curves.
Yeah, the greens are the simple closed curves. So I'm creating, from this picture over here, a bunch of simple closed curves which record how the Julia set cuts the roots apart. And all you do is you go near the edge of each component and you draw a bunch of curves which are quite near the edge and away from the roots. And so this picture of simple closed curves records sort of the combinatorics of how the Julia set cuts the roots apart.
How many do you draw?
Well, I drew a fair number. I mean, usually there will be sort of an uncountable, possibly an uncountable number. But in any case, there's only a finite number which are non-trivial. That is, a finite number of distinct ones which are non-trivial. Okay, well, in any case, there's a way to record the combinatorics of the Julia set just in terms of a collection of simple closed curves. Now, there's a theorem which says if the algorithm doesn't fail, this whole picture sort of moves along continuously and comes back to itself. That means this whole system of simple closed curves moves along and comes back to itself. But the group, by assumption, is irreducible. Therefore, it's preserving this system of simple closed curves. So it follows that there are no non-trivial simple closed curves in this partition which I constructed. That is, every curve in this picture has to only enclose at most a single puncture. Okay, and the reason again is because this group is assumed to be irreducible. That means it preserves no interesting system of simple closed curves. So for example, these two curves which I've drawn here couldn't possibly occur if this was a good algorithm over a tangled subset. Okay, then with a little combinatorial topology, you argue that that implies there must be a single component of the Julia set which separates all four roots from one another. So we call that component K. Well, then at the beginning of the talk, I mentioned that the automorphism group of the dynamics, when restricted to a component, is finite, and that implies that all this twisting that's going around must actually be finite. So once you get this separating component, it completely rigidifies the situation, and you can barely make any grades at all. You can't even interchange two roots cyclically. So somehow the finiteness I discussed at the beginning of the talk says that once you have a separator, the situation is very inflexible, and consequently the monodromy group must be finite. Well, there's a couple more things to say, but maybe I'll stop here and just mention a problem. Yeah.
I see that's enough to ensure these finiteness is the function part.
Yeah. There are three conditions on the group.
Right.
One is that transitivity,
right,
irreducibility, and finiteness. And this
here you get, when you come around, that you're sort of the identity of definite things on this connected set. And this implies you're the identity in the mapping class group of 4 points.
Right, because and this component separates the 4 points from them. So
Yeah, so
any
it
metric that goes on is selected from
Right.
that set.
contains a slot to them.
Right. So, what we conclude with an interesting problem, this discussion shows that you not do the following. It's, as just mentioned here, can weaken your dependence on T, continuous, and still can't find robust algorithms that work in degree 4 or more.
Why is that?
Sorry?
What's the idea of that?
That's basically what this proves. Why can I get continuity?
You didn't use any. You only use it.
It's basically topology. It's basically a touch argument. In any case, the argument says, if we consider the following problem. Let me state what the problem is and then describe how the discussion aid reflects on its solution. So the problem is the following. Given 4 points on the Riemann sphere, find a map P of Z such that, or given 4 points A, such that, let me just say this roughly, A is equal to the attractor of T. Now what I mean by that is I'm going to specify 4 points on the sphere, and I'd like you to design a map such that under iteration, some points are attracted here, some points are attracted there, some points are attracted to the third point, some points are attracted to the fourth point, and every point is attracted to one of the 4 points. Or almost every point is attracted to one of the 4 points. Okay, so that would mean this set coincides with sort of the points to which you tend to under iteration for almost every point on the sphere. And the reason this is an interesting problem is that the discussion I've just described says that there's no way to do this in such a way that the rational map you get depends continuously on these 4 points. Okay, so somehow you have to, in doing this construction, you have to make a choice at some stage. And the choice can't possibly be made in a continuous fashion. So this is the general rubric for this problem is construct a rational map with a prescribed attractor. And the discussion is that can't be done in a continuous fashion.
Can it be continuous on the universal cover of the space of 4 points?
Yeah, sure. It could be.
Could be continuous.
Yeah. Yeah, okay. Well, there were a few other things to say, but...
The argument you gave here didn't seem to use the fact that it was robust.
It doesn't. There's 2 terms. The first thing is that every algorithm, robust or not, fails on a tangled set. There's no assumption of robustness in the first conclusion. But every purely iterative algorithm fails on this set without any assumptions. The point is, if I
That's just being rationally coefficient.
yes.
No continuous one as well.
Yes. Right. That's just because you want to use open something measured. So I believe that robustness is not really necessary for this conclusion about failure when you weaken the dependence on P to continuous. It's just that the proof more naturally works when it's extending that.
What was the point here where it breaks down to 3 points?
Oh, it doesn't break down for 3 points.
But the group is finite. The Frey group is finite.
No,
Well, I mean, that can get the algorithm to 3
yeah.
qubits, so...
We can't do the analogy.
The theorem is greater than 3. Isn't it?
No, well, okay.
It's automatically greater than 3.
Okay, what is a tangled set? Well, for one thing, a tangled set, this group has to be infinite. And it's a subgroup of the mapping class group of the d times punctured sphere. So if you think about a 3 times punctured sphere, it turns out there's only a finite group of homeomorphisms up to isotopic. In fact, it's just the symmetric group on 3 elements. That is, you have a homeomorphism which fixes 3 points on the Riemann sphere, and in fact it's isotopic to the identity of the whole. It represents faithfully how it mutes functors. And that's why it was possible to make an algorithm for cubics in some set of y. So there aren't any tangled subsets when D is 3 or 3.
Error to quantify is no problem. Is any set A before point?
Yeah. Oh yeah, sure. You can easily write down, open sets of 4 points, a point of 4 points that you can tractor there. But the question is to cover the set of configurations of 4 points. But, I mean, let me give you an example.
Am I one selected 4 points that you can't write down such a
Right, a universally unsolvable polynomial. Let me give you an example. If you take a polynomial of degree 4, the 4 real roots, then Newton's method is guaranteed to be generally convergent for this configuration of points. So given any real points, you can find a rational map such that this is exactly a tractor. And we just take Newton's method for the polynomial as root as points. Now, this indicates, incidentally, a possible way of going about trying to solve this. Let me mention that possibility. So you write down P of x is the polynomial with roots at a. And then you apply Newton's method to this polynomial. So what does Newton's method do? It's the transformation T of z minus P of e over P prime of z. So it's basically the identity and then a correction term which is meant to be closer to the root. Now it turns out that there are many cases where this does not have the problem that the tractor coincides with the root, at least when the degree is 4 or more, actually 3 or more. One way to try to improve the behavior of this method is to throw in a caution factor here. Throw in a small constant making this correction term small. So you tend to try to inch your way towards the roots instead of going there in large steps. So what you might have solved the problem is saying that fixing the polynomial, this becomes generally convergent once you take this h small enough. Now it turns out that can't really be true, because then you will be able to do this in a continuous fashion. But what may be necessary to do is make h slightly complex. So make it 0.01, and then there are places where even that fails. And then you perturb it a little bit to the right or the left. It's possible that choice of the right or the left is exactly the discontinuity you need to make this instruction. So that's a candidate for having to carry out this procedure. Hasn't been well investigated yet.
I got lost. It looks like it's a candidate. I don't even have the attempt.
Your point
I see you're suggesting that you look at a very special sort of function, but that function is going to have to be.
and there's going to be some polynomials where you just make it smaller and smaller, and then you make a choice of whether to perturb it to the right or the left in the complex plane. Make it slightly positive, imaginary, or negative. And because that choice of perturbation will not be possible to make continuous fashion. That'd be the.
In other words, you don't really know what the lack of continuity is.
I don't really know where it's going to be. I can tell you on which sets it's going to have to be discontinuous, but I can't tell you exactly how.
Is there a picture that goes with that? Why you kind of perturb it to the right or to the left? Can you see,
Yeah,
can you see a picture that
Sure.
that?
Sure. This method very closely approximates using the following two. This method is like it's the same as taking out the value of the polynomial square and trying to find the minimum of this, point on the gradient. And the kind of problem you can run into is that so these are the roots of the polynomial. There are critical points as well. And the way this flow works is that you start out at infinity and you tend to flow towards a root, and probably you might flow toward a critical point of the polynomial, at which point the whole process stops. You're sort of at that. And then, now to show Newton's method is generally convergent, it finds that the critical points of this function tend towards roots. It turns out it's a general criterion for robustness of Newton's method. So you can imagine that as h is small, the critical points are more nearly following this flow. Now, the problem is, it might be true that the critical point is exactly on the flow line which terminates on this station saddle here. And so what you do, by changing h slightly, that amounts to taking this gradient vector, perturbing it so it has a slight into it. So instead of coming straight in at the root here, it sort of spun around very slightly. And that will have the effect of, instead of letting this straight into the saddle, it'll veer off slightly one side and go to a particular root. Okay, so that's sort of the dynamical picture. You just have to perturb these situations where something's going to happen.
Any failure of this Newton type method that comes from a critical point?
Well, I'm sure what you're...
Yeah, I mean, you're saying the critical problem here.
Yeah, I mean, well, let me just give you an example. If you had this polynomial and curved it a little, what would happen is the following. You would have bad behavior because you get stuck under a minima of that. Now, it turns out that you can find this minimum because one of the critical points of this function, this rational function, is attracted to this minimum. Okay? So if you can show that none of the critical points fall into a funny song, where they all go to the roots, and then you get behavior. I mean, this is all, you also sort of the need of behavior, because if you start on the real axis, well, then you stay on the real axis, really, from the complex roots of this polynomial. So there's a prediction you sort of choose to go up and go in the upper half plane or the lower half plane.
And success is maybe find any root, not all the roots.
Now, in this case, you have to find this is the concept of tracks. Either write down a function that has factor 10 and it gives that. How's that going on?
In the original discussion.
The original discussion, transitivity, I decided to ensure that you have a track at one point. Now, well,
Why don't we see now in the we'll talk about Hagen-based variance of smooth time we see electricity that go like cookies